Hi, so we're going to do the second video in this P15 electromagnetism, using electromagnetism. So the section we're looking at today is this section. So we've got Fleming's left-hand rule. Spelt it wrong. Motors, that's supposed to say, sorry. Loudspeakers and generators. So we're going to look at Fleming's left-hand rule first, and this is the specification, so you can pause if you want to read it. Okay, so Fleming's left-hand rule. Electromagnetic induction. Induction means to start, okay? So electromagnetic induction means using electricity and magnetism to induce or to make or to start a current, okay? So, so the premise of Fleming's left-hand rule is that when a current carrying conductor, remember that's the posh way of saying a wire, is placed in a magnetic field, the magnet and the conductor actually exert a force on each other, according to Newton's third law. And because the magnet is usually quite heavy, it doesn't move, but because a wire is quite light, then it does move. So this effect is called the motor effect, and it's used to make electric motors. And the direction of the force can be determined using Fleming's left-hand rule. So Fleming was the person who did a lot of work on this, and he made an equation which we're going to look at. And you use your left hand to determine what direction the wire will move in. Now we will do lots of work on this in class, okay? But you can draw the hand down and write them down. But the way I remember it is, so you make a gun, okay, with your left hand. So you've got your force here. Force field. So I remember it as force field as a saying, okay? And they're at right angles to each other, and then you need your third finger to be at right angles to those. So it comes here. So if you point the gun at someone, not in real life obviously, and then there's your trigger finger. Force, field, current, and they're all at right angles to each other. So you can see there's a right angle there between those two, and there's a right angle between these two, and then a right angle between these two. That's Fleming's left-hand rule, and you've got to try and move your wrist around with it, okay? So you might want to press pause and draw that down. Okay, so Fleming's equation is force equals magnetic flux density times current times length. And the force is measured in newtons, and the magnetic flux density, this is just a really posh way of saying the strength of the magnet, is measured in something called Tesla, which is what the electric cars are named after because they use magnets, electric motor. So you've got T for Tesla. Current is measured in amps and length is measured in meters. And this is quite nice because magnetic flux density is given the symbol B, okay? Magnetic flux density. I don't know why actually, but yeah, so it spells a lovely equation, F equals Bill, okay? And so force is measured in newtons, magnetic flux density is measured in Tesla, current is measured in amps or amperes, and length is measured in meters. And you've got a triangle here, but it's got an extra bit in the middle than normal. Okay, so we use that to make motors. This is what you need to know about motors. So to make a motor, what you need is a power supply to supply some electricity, okay? So to make a motor, you need a power supply. And you have this thing called a split ring commutator. It's here. It's just a ring that's a connection. And the reason it's there is to keep the electricity flowing one ray around this circuit. Okay, so it just keeps it flowing the same way. And now the current is at right angles to the magnetic field. So the current's here, and the magnetic field is going across north to south. So they're at right angles to each other. So the current's going into the page, and the magnetic field is going across here. Okay, and the induced magnetic field in the wire and the permanent magnet interact and they create a force. And if we look at Fleming's, let me move me here. If you look at Fleming's fingers again, okay, so you've got your force, field, current. So the current is going into the page, okay, and my field is going north to south, so it's actually going that way. So my current is going into the page. So here's my finger going into the page. My field is going this way, and so one side of it's going to go down, which is the left-hand side, this side here. Right-hand side, sorry, here. On the other side, so the current's coming into the page. On the other side, the current will be coming out of the page. Okay? Out of the page. So I've got the same setup, but my current's coming out of the page. This is where it gets tricky. My current's coming out of the page towards me. My field is going across still, so my force is up. So the effect you get is a force up on one side and down on the other, which makes it spin. Okay, so the force on one side of the coil is in the opposite direction to the other side of the coil, and it makes the coil spin. And you can see that here. Well, this one's going the opposite way around. It just means the current's flowing the other way around. You can see here you've got negative and positive, and this side you've got positive and negative. So it just makes it flow the other way around because you made the current reverse. But you can see the idea. One side gets pushed up and one side gets pushed down. And in lesson, I'll try and let you make a motor so you can see that in action. Okay, so looking now at induced potential. So remember, induced means to make or to start, and potential is to do with voltage. So if you want to make a loudspeaker work, this is what you do. This is a picture of a loudspeaker. I'll go through the sections in a minute, but we'll do this. So an electrical signal is made by the device and the loudspeaker is connected to. So here we've got an input voltage signal here. So this is your signal coming into your speaker. Okay. Inside the speaker there's an electromagnet. So here's the electromagnet. So you can see the magnets here, and then the coil is around this bit. So here's your electromagnet. Okay. Now variations in the current change as the current change the strength of the electromagnet, because you've got a variable supply coming in here. So your speaker is changing the current in here. Your magnet here gets stronger and weaker. Okay. Now the cone is attracted to the electromagnet. So here's your cone, and it's attracted, so it'll have a metal bit on it here that's attracted to the electromagnet. And the amount it's attracted by depends on the strength of the magnet. So if your magnet is going from strong to weak, 0 to nothing, what it does is it makes it do this. Pulls it in, or sometimes it will pull it in a little bit, or then a lot, okay? And it will change the frequency as well. So it makes the cone vibrate backwards and forwards. And the vibrating cone makes pressure waves in the air, which we then hear as sound. So I will go through this with you in the lesson, but it might be nice for you to have this information written down for that lesson. Okay, so then we're going to look at the generator effect. So this is generating electricity. So generator effect looks a lot like a motor, except for instead of using electricity to make the coil spin, you have to use something else. The easiest one I find to think about is a wind turbine. So how do you generate electricity? If you move a magnet near a conductor, or there is a change in the magnetic field in the conductor, then a potential difference is induced across the ends of the conductor, i.e. you make one side positive and one side negative. So if you watch the picture here, you're moving the conductor in the magnetic field, and that will create a potential difference. So one side here positive and one side here negative, because what it's doing is forcing the electrons to move around the circuit using that force, that Fleming's left-hand rule force. Now, a force is applied to the coil. So often in a turbine you can use wind, so you apply the force to make it spin. In a water turbine you might use the waves, or you might use, in a hydroelectric power station, you might use water falling, okay, through the turbine. So you have to apply the force to make the coil move. The movement of the coil is at right angles to the magnetic field. So you can see here the magnetic field goes north to south, okay, and the coil itself is at right angles to that. Now the coil will cut the field line. So if you imagine the field lines going here north to south, the coil, as it spins round, will be moving through those field lines. Okay, there is a potential difference induced across the ends of the coil. So again, you get a positive one side and a negative the other. And because you have a positive one side and a negative the other, it makes the electrons move around the circuit, and so you generate a current. So because the coil spins, you actually get, unless you use a split ring commutator, you actually get AC. So you will get the current going one way as it's moving up, and then as it's moving down, the current will move the other way. So you get alternating current. If you want to make more electricity that way, then you need to increase the speed of the movement. So on a windier day, you get more electricity. You need to increase the strength of the magnetic field, so using stronger magnets, okay? Or you need to increase the number of turns in the coil of wire. So I've got one coil here, so if I did 2, I could double the effect, 3, 4, 5, 6, 7. So the more coils you have, the more electricity you make. And factors that affect the direction of the induced potential would be the direction of movement. So if you spin it one way, you get electricity one way. If you spin it the other, you make it the other way. And the direction of the magnetic field. So if I reverse these and made north to south, then the current would flow the opposite way around. Okay? So pause me and write down that information. Draw the pictures. You also need to know how a microphone works because it uses that idea. So microphones turn, so rather than a speaker, so speakers turn electrical energy into sound energy. Microphones turn sound energy into electrical energy. And they work a really similar way as a speaker, but just the opposite direction. So you provide the force, okay, instead of electric current. So when someone sings, sound waves, which are longitudinal pressure waves, create vibrations in a diaphragm. So here's your diaphragm, and there's your sound waves coming in. Okay, the diaphragm is connected to a coil of wire, which is here. Okay, and the vibrating diaphragm moves the coil backwards and forwards. This coil will move backwards and forwards. And then this is a magnet. So you're moving a coil of wire in a magnet. When you move a coil of wire in a magnet, the same as a generator, okay, the coil of wire will cut the magnetic field lines, and this will induce a potential difference across the ends of the wire. So here's your wires, and you'll have a positive and a negative. And because you've got a positive and a negative, that will make the current flow. It forces the current to flow, okay? And the wire is attached to complete a circuit, so AC current can flow. So when it moves in, the current will move one way, and when it moves back out, the current will move the other way. And then your amp or whatever you plug it into can then turn it into an electrical signal, which can turn it into, convert the speaker back into sound. Okay, that's it. I realise this is quite difficult, and basically you've just got to learn to write about these things, so I'll give you some practice of that in lessons.